Good afternoon. Today we are going to see about the methods of determining the voltage regulation in an alternator. Before going to the topic, first I will explain the basics of an alternator. So there are variety of names for the alternator. Alternator is nothing but alternating current generator, or it is called as AC generator. From the alternating current generator, we derived the name as alternator. So from this, we derived the name as alternator. So sometimes it is called as AC generator. So one more name is there, that is called synchronous generator. So there are a variety of names for a single device. When it is called as alternating current generator or alternator, when the machine is working independently or it delivers its own load, or sometimes technically it is called as when the alternator is delivering to its own load, or at the time of islanding mode, it is called an alternator. When it is called as synchronous generator, when many number of alternators are connected in parallel, or some other machines are connected in parallel with the same machine, during that time that machine is called as synchronous generator. So the name is the same, depends upon the application, it is called as alternator or the synchronous generator. Then one more reason is that why it is called as synchronous generator. The generator must always runs only at the synchronous speed. What is mean by synchronous speed? So the formula for the synchronous speed is Ns is equal to 120 F by P. How we obtain this formula? First, I will explain you the basics. If you place a conductor within a magnetic field, the conductor comes across the north pole, the current direction is assumed as dot. If the same conductor comes under the south pole, the current direction is mentioned as cross. So whenever the conductor complete one revolution, when it comes under the north pole, the current direction is mentioned as dot. When it comes under the south pole, it is opposite to the previous one. So to create a one cycle of waveform, one pair of poles is necessary. So when it comes under the north pole, it creates the positive sign. It comes under the south pole, it creates the negative sine wave. So that the number of cycles per revolution is equal to the number of pair of poles. So it is nothing but P by 2. Then the time taken to complete a one revolution. So the number of revolution by time, or it is mentioned by seconds, N by 60. N is nothing but the speed which is measured in revolution per minute. The 60 is the number of seconds per minute. If you are multiplying these two, P by 2 into N by 60, it will give Pn by 120. So if you are multiplying these two, we will get the number of cycles per second. The number of cycles per second is nothing but the frequency, F. So from this equation, we may derive the equation for the synchronous speed. So N suffix S is equal to 120 F by P. Here Ns is the synchronous speed. F is nothing but the frequency of the supply. P is the number of poles. Not only for the alternator, for any machine, the number of poles must be a even number. So the minimum possible even number is 2. As per our Indian standard, the supply frequency is 50 Hz. If we are substituting these two in this equation, we will get the maximum possible speed of our Indian alternators. So instead of F, here we can substitute 50. For P, we will substitute 2. The final answer is 3000 RPM. So the maximum possible speed of our Indian alternators is 3000 RPM. So we are always making our generator to run only at the synchronous speed. One more reason is there. Why it must be always runs only at the synchronous speed? If we maintain the supply frequency as constant as per our standard, it is 50 Hz. To maintain the frequency as 50 Hz, our machine must run only at the synchronous speed, then only we will get the standard frequency. Next thing. So what are the basics of an alternator? Alternator is nothing but, we already told that it is the AC generator. The generator is an electromechanical device. It converts the mechanical energy into electrical energy. It may be AC generator or DC generator. It converts the mechanical energy into electrical energy. It works on the principle of Faraday's law of electromagnetic induction. So as per the Faraday's last statement, we need minimum of 2 elements to create a single sine waveform. One is the magnet, another one is the conductor. So as per the Faraday's law, we can induce the EMF in any conducting material. Either the conducting material is the movable one or the magnet is the movable one. Among these two, any one must be a stationary part, other one must be a rotating part. So as per our AC generator is concerned, the magnet is considered as the rotor. The conductors are placed in the stator. So from the name itself, we can able to understand that stator is nothing but stationary part of the machine. The rotor is the rotating part of our machine. The EMF is induced in the stator part here because the conductors are placed in the stator. There are two types of EMF. We can classify the EMF, but here the EMF is induced in the stationary part. It is considered as the statically induced EMF. The EMF which is induced in the alternator is considered as the statically induced EMF. Next. The winding which is placed in the stator is always, here we are using a 3-phase winding. There are variety of categories available in the 3-phase winding. Mostly we are using a double layer short pitched double layer short pitched winding. We are always using a double layer short pitched. One more category is there, it is the distributed winding. So distributed double layer short pitched windings are always used in the stator part. As per the three-phase connections, here we are using a star connected winding. Star connected winding with the neutral is grounded. So these are the basics about alternator. Why it is called as alternator, what are the different names, what about the construction of the alternator. Next. We will concentrate on our topic, that is the voltage regulation, determination of voltage regulation. So not only for the alternator, we are finding the voltage regulation for the transformer also. Because the alternator and the transformers are considered as the sources for transformer and the alternator, and also for the DC generator. We are calculating the voltage regulation. What is the necessity? Why we have to calculate the voltage regulation for the device? Because these are considered as the sources. From this only we are getting the power supply. The motors are considered as the load. No need to find the voltage regulation on the load side. So we are always calculating the regulation for the alternators. What is the necessity? Why we are calculating the voltage regulation? All the appliances, not only in domestic purpose, in the industries also the appliances are connected only in parallel. If it is the parallel circuit, the voltage rating or the voltage across the any device or any terminal is always maintained as constant. So the minimum voltage which is required for the fluorescent lamp to work is around 180 volt. If it is a single phase supply, the input we are getting the voltage as 230. If it is the three phase supply, the voltage rating is 415. So all the appliances are designed to operate at 230 voltage if it is the single phase appliances. If it is the three phase load, all the loads are working at 415 voltage. So the tolerance limit for the voltage is 10%. It may be deviated plus or minus 10%. So that all the appliances are connected in parallel, we must maintain the voltage as constant. If any deviation in the voltage, definitely it will affect the performance of the machine as well as the lifetime of the machine also. So we are calculating the voltage regulation for all the sources. So what is the formula to find the voltage regulation? So it is the formula E0 minus V by V into 100 if it is percentage of voltage regulation. What is E0? E0 is nothing but no load induced EMF. V is the terminal voltage at loaded condition. So what is the reason why there is a drop in voltage whenever if you are adding the load to the circuit? So there are three reasons. These are the causes for the voltage drop. First one, the armature resistance in the stator side. This Ra is the most important factor. Next one, the leakage reactance, the last one, due to armature reaction also. There will be a voltage drop in our circuit or in our load. So how to calculate the voltage regulation? For that we have the different methods. One is the direct method. Another one is indirect method. So the direct method is nothing but load test on three-phase alternator. We can find the voltage regulation by the direct test if the alternator voltage rating is less than 5 kVA. If the power rating of the machine is greater than 5 kVA, we cannot use the direct method. We will go for the indirect methods. 4 methods are available in the indirect method category. First one, EMF method. The expansion is electromotive force method, or it is called as synchronous impedance method. Next one, MMF method. MMF is nothing but magnetomotive force. EMF is electromotive force. MMF is magnetomotive force. The another name for the magnetomotive force method is ampere turn method. Ampere turn is nothing but the unit for the magnetomotive force. Third one, ZPF method. ZPF, the expansion is zero power factor method, or it is called as Pottier method. The fourth one, ASA method. The expansion of ASA is American Standard Association method. It is the modified MMF method. So next question will be arising in our mind. Why we are not going to direct method? Why we are choosing the indirect method? For our understanding purpose, we will consider that if it is the 5 kVA machine, 5 into 10 power 3 volt ampere, we are assuming that the voltage is around 400. The ampere rating is around 12.5 amps. Next, the direct method can be applicable only for the low power rating generator, as well as we can able to use the unity power factor load here. If the power factor is unity, the 5 kVA is nothing but VI is volt ampere. It is nothing but the apparent power S. If you are calculating the real power, VI cos pi is the power factor. For the unity power factor, the power factor value is 1. The 5 kVA is multiplied with 1. We are consuming 5 kilowatts of power. We are not going to use this for any specific applications. We are going to use this power consumption only for testing the machine. If the power rating is more than 5 kVA, if we are using it by the direct method, the entire power which is used for testing is entirely wasted. To avoid the power wastage, we are going for the indirect method. So first, I will explain you the EMF method, electromotive force method. To test the machine by the indirect method, we need the 3 test data. The first one, open circuit test data. Open circuit test. The second one, short circuit test. The third one, we need the measurement of armature resistance or armature resistance. It is nothing but RA. We can measure the armature resistance. There are two ways. One, straight away we can use the multimeter, or we can use the voltmeter ammeter method. By applying the reduced DC supply to the stator, the single phase winding, or for example, if it is the alternator's stator winding, we are going to give the DC supply across a single phase. We will measure the armature resistance per phase value here. Either we can use the multimeter or we can use voltmeter ammeter method. For the first two tests, there are different names. The open circuit test is sometimes called as no load test. The short circuit test is sometimes it is known as full load test. First, we will see about the open circuit test, how to conduct the open circuit test in an alternator. It is shortly called as OC test. Here we are not concentrating on the prime mover side, we are concentrating only on the alternators. It is considered as the stator winding of the alternator. It is star connected, R for R phase, Y phase and B phase. All the other end of the phases are connected together. It will consider as the neutral. One more winding which is placed in the rotor, it is called as field winding. The terminals are mentioned as F1, F2. We will give the DC supply to the field winding through a variable resistance or through a rheostat. The meter used to measure the field current is MC meter, moving coil meter. The supply which is given to the field winding is always DC supply. Initially, the prime mover is connected with the field. The prime mover may be IC engine or the DC motor or any AC motor. By using this, we will bring our generator to rotate its rated speed. Once if it is fixed throughout the test, we are going to maintain the speed as constant. For example, in our laboratory purpose, we are using if the rated speed of your armature is considered as 1500, we are going to keep it as 1500. Then we are going to vary the field rheostat. First, initially it is kept at maximum, then we will vary it, we will cut the resistance step by step manner. Here we need two meters. One is the ammeter which measures the current to the field winding. Another one is the voltmeter which measures the voltage across the stator or the alternator. Here the voltmeter used to measure the voltages moving iron meter. The range is 0 to 600. If the alternator's rated voltage is 415 means we will use this range 0 to 600 volt. Initially rheostat is kept at maximum, then we will vary it step by step. Then finally it will comes to minimum. But we will vary the field rheostat to up to the alternator generates its rated voltage. Once the voltage across the voltmeter reaches the rated value, we are not going to vary the field rheostat. This data is required from the OC test. The field current and the open circuit voltage per phase. Here the voltage measured between the alternator is line quantity. To find the per phase value, the line value is divided by √3, we will get the phase quantity. Why we are calculating or why we are converting it into phase quantity? The resistance which measured in the voltmeter method is the per phase resistance. So we are going to calculate the voltage regulation for the per phase values. It is the first test, it is open circuit test. Then we are going to conduct the short circuit test. For the short circuit test, in the open circuit test, the terminals of the stators are kept at open. In the short circuit test, all the terminals are short circuited through a low resistance ammeter. Here the ammeter used to measure the current is MI, moving iron ammeter. Here it is moving coil meter. It measures the DC quantity, it measures the AC quantity. In the short circuit test, first we will keep the alternator at its rated speed. Then by varying this rheostat, we will bring the volt current as its rated current or the full load current. Whenever the ammeter which is connected at the short circuit terminal shows the rated current, we will stop the variation in the voltmeter, variation in the rheostat. Then these are the data obtained from the OC test. From the short circuit test, we will get the data which is the field current and the short circuit current. Then we already measured the armature resistance value here. RA value is already found. By using these three values, by using these three data, we can able to find the voltage regulation. How to find the voltage regulation? By using this data. First, we are going to plot the graph between the field current and the open circuit voltage. The field current is taken in the x-axis. The open circuit voltage per phase value is taken in the y-axis. We will draw the graph between the x-axis and the y-axis. It is nothing but the OCC curve. It is called OCC, open circuit characteristic curve. This curve is drawn between the field current versus the open circuit voltage per phase. If you are increasing the field current value from 0 to its maximum, once the voltage reaches its rated value, if it is the per phase value, it will never come as 415, it is around 230 voltage. Once it reached the value, after that if you are varying the field current, there will be no change in your voltage. So after the saturation, if you are varying the field current, we will not get any variation in the voltage graph. So it will be flattened like this. Then by using the short circuit test, we are going to plot the next graph. It is also going to plot in the same graph sheet. The x-axis value is the same. In the y-axis, we are going to take the short circuit current. For particular value of field current, we will get some short circuit current value. So it is the short circuit curve. It is drawn between the field current versus the armature current or the short circuit current. First, we will take the rated full load current. First, we will make that point. From that, if you are projecting it in the x-axis, it is projecting to intersect the y-axis also. It intersects your OCC curve at some point. That voltage is considered as the open circuit voltage. This current is taken as the short circuit current. By using these two, we can able to find the synchronous impedance value. Synchronous impedance Z suffix S is nothing but the open circuit voltage per phase by the short circuit current. At the same excitation. It is most important. So we will take the value of the open circuit voltage as well as the short circuit current for the same excitation. By using these two values, we can able to find the synchronous impedance. The value is in ohms. The unit for the synchronous impedance is ohms. The formula to find the open circuit induced EMF E0 is nothing but V cos pi plus IA RA whole square plus V sin pi plus or minus I into X suffix S whole square. Take the square root for these answers. What is the necessity? Why we found the synchronous impedance value here? We know the synchronous impedance from the EMF method. From the measurement of the armature resistance, we know the RA value. By using these two, we can find the synchronous reactance by using this formula. The square root of Z square minus RA square, we will get the synchronous reactance value. We can able to substitute that value here. What about the power factor cos pi? If you are calculating the voltage regulation for the power factor of 0.8, the power factor is purely depends on the load. There are variety of loads. As per the electrical circuit is concerned, it is classified into three: resistive load, inductive load and capacitive load. Whatever may be the invention in the world, all the loads comes under this category. Either it may be the resistive load or inductive load. If you are using any type of induction motors, it is considered as the inductive load. Any type of resistive material is added in your circuit, that is considered as the resistive load. If it is the resistive load, the power factor is unity, UPF. If it is the inductive load, the power factor is considered as the lagging power factor. If it is the capacitive load, the power factor is leading. For our assumption, here we are taking the power factor as 0.8 lagging for the inductive load. We will substitute 0.8 here. The per phase voltage is substituted here. IA is nothing but the armature resistance. The full load armature current is substituted here instead of IA. RA is the armature resistance value. Then, if you are substituting all these values, we will get the answer in volt. The no load in volt. By using this, we can able to find the voltage regulation. If we are using this formula to find the voltage regulation, our load is the resistive load, our answer will be in the voltage regulation is positive. If we are finding the answer for the inductive load, it is also positive. If the load is the capacitive load, we will get the answer in negative. So, the voltage regulation is negative for the capacitive loads. Then, here we added two signs, plus or minus. Plus is used for the inductive loads because inductive load consumes the reactive power. Capacitive load delivers the reactive power. So, the negative sign is added for the capacitive loads. The regulation which found by using this EMF method is considered as the voltage regulation found from this EMF method is always greater than the actual value. So that it is called as pessimistic method. Why it is called as pessimistic? At the low saturation, the synchronous impedance value is always high. If you are substituting this impedance value here, we will get the voltage regulation which is greater than the actual value. So that it is called as pessimistic. What is the meaning for this? We never get the accurate value. The value which we got from this EMF method is always greater than the actual value. For the EMF method also we can able to use the same graph. Instead of finding the synchronous impedance, here we will calculate the resultant field current for the EMF method. So we will conclude with this. We have different types of load, power factor for that load, then the voltage regulation. If the load is the resistive load, the power factor is unity, the voltage regulation value is in positive. If the load is the capacitive load, the power factor is leading power factor, works at the leading power factor. The voltage regulation is negative. Why we got the negative voltage regulation? As per the formula, E0 minus V by V into 100. It is the formula to find the voltage regulation. When we will get the negative value, if the voltage at the loaded condition is greater than the voltage at the no load condition. So, the voltage value is greater than the induced EMF at the no load condition. We will get the answer in negative. What is the reason for that? We must know about the armature reaction. Then only we can able to answer this. If the capacitive load is connected in the alternator, final effect from the capacitive load is magnetizing effect. Because of the magnetizing effect, the flux which present in the air gap is higher than the normal case, so we will get more amount of voltage at the loaded condition. It is the reason for getting the negative voltage regulation at whenever if you are connecting the capacitive load. The final one is the inductive load. Inductive load is connected, the power factor is lagging. We will get the regulation in positive. One more choice is there. One, we are getting the voltage regulation at positive, or we will get the voltage regulation at negative. At some cases, the voltage regulation will become zero. When we will get the zero voltage regulation. During the capacitive load, if you are connecting the capacitive load, for some particular power factor of leading condition, we will get the zero voltage regulation also. When we are getting the zero voltage regulation means whenever the E0 value and the terminal voltage are equal, no load induced EMF at the terminal voltage at the loaded conditions are equal, we will get the zero regulation. There is no deviation between your voltage at the no load to the full load, so we are getting the voltage regulation at 0. So finally I will conclude within few minutes. We have different methods. I have explained you only the EMF method alone. EMF method will give the answer which is higher than the actual value, so it is called pessimistic method. The MMF method is called optimistic method. Why it is considered as optimistic? The E0 value found from this is always less than the actual, so we will get the reduced regulation here. The technical reason for this is in the MMF method, we are considering the leakage reactance is also armature reaction effect. The leakage reactance is also added with the armature reaction effect, so that we will get the answer which is less than the actual value. Next one is the zero power factor method. By using this Portier method, we will get the accurate value. The last one is ASA. It is the modified MMF method. So from this we can able to conclude that alternator is a generator which generates the electrical power. The electrical power which is generated from the alternator is always maintained in within the tolerance limit. So specifically we are here concentrating only on the voltage. The voltage must be within the tolerable limit. If there is any change in the terminal voltage of the alternator, it definitely affects the appliances which are connected in the circuit. Not only the performance of the appliances, it will affect the lifetime of the appliances also. So we must maintain the voltage, terminal voltage of the alternator within the tolerable limit. Thank you. Thank you very much.